About our discussion of atoms. So that we've talked about hydrogen, and I've made all of these claims about that the hydrogen atom teaches us a lot about the entire periodic table. And this last concept, I think, really drives that point home. And we discussed it a little bit last class, but let's just start over again and think about it. And this concept is what's called electron shielding. Right? If you've ever studied NMR, you've probably heard of this concept of shielding. It's very similar, but this is a different kind of shielding. This is an intra-atomic shielding instead of a shielding between atoms, which is what happens in NMR. This is a shielding of electrons from each other within a single atom. So the way I want to look at this concept of shielding is where we move from one atom. So as we add protons, we create bigger and bigger atoms. We're going to hit a point, right, where we fill a valence shell. Right? Helium, we fill the first valence shell, 1s2. Then we move on to lithium, and we fill in the next shell. Right? The valence shell now becomes the n=2 levels in lithium. And I want to look at that point, right? And how does the new valence electron see the atom that has this core that is completely filled, right? What does the 2s electron in lithium, what does it see when it looks deep into the system, into the atom, right? How do those 1s electrons affect the 2s electron? And shielding is the key idea here. So what we're going to do is we're going to treat this fully filled kind of core, all right? So think for helium, like a helium core, right? 1s2, it's got some protons in it, and it's got 2 electrons in the 1s orbital. Right, we're going to call this, we're just going to think of this as a giant ball of charge. Okay, so think of the helium atom as just a big ball of charge. So we'll draw a little circle here. Like that, and then at the interior of this circle is a nucleus, right? A nucleus of some number of protons. Right, but we'll say it has Z plus charge. Okay, and we're going to, and within this shell, right, this shell, which is a physical object, the center say this is lithium, Z is 3 here, because there's 3 protons in lithium. That there's also all of the core electrons are contained within this shell. Okay, so we'll think about the core electrons having some length scale, right? They're contained within this sphere. And then every other electron that gets added to it, hopefully, will go on the outside, right? It will observe the charge distribution from the outside of this circle. But we should consider what happens if we bring the electron in. Right? What if the 2s electron, for some reason, we could add it to the core? What would it see compared to what we would observe from the electron's point of view if it were outside this ball of charge? Okay, so let me define a few things here. First, we'll say that the distance between the edge of this core and the protons, or the nucleus, is r0, right? Doesn't matter what that length scale is, it's just r0. And within this shell, we'll have the entirety of the core electrons inside of it. Right, so there's electrons, some core electrons in here. Right, there's our core electrons. And we'll say that there are Z-1 of them. All right, so there are, inside of this ball, there is a positive charge of Z plus and a counteracting Z-1 negative charge, right? Because Z-1 electrons provide Z-1 negative charge. So the net charge is the sum of these two. So the total charge is going to be, I'll just color code it, Z minus, because again, we're subtracting off the electrons, they have the opposite charge, Z-1. So the total charge of this ball is +1. Okay? So what that means is that this ball effectively, The way you can think about this is that it's a really, really big proton, right? Effectively, from long distance, this just looks like a ball of charge that's +1 charge, right? It just looks like a big fat proton. Okay? And what I want to do is I want to ask the question, when I stick a new electron in here at some distance from the core, what charge does it feel? Does it see the atom, the interior of the atom, as this +1 ball of charge? Or does it see the fact that there are some electrons in there and a much larger positively charged nucleus? Does it see some fractional charge that would be between +1 and Z+? Right? Does it see the entirety of the positive charge inside of the nucleus? So I'm going to introduce what we call a test charge, which is just an electron. We're just going to put an electron in there. So introduce a test charge, which is just a point of -1 charge. All right, so you can just think of it as an electron at some position r. Okay, and we have two options where where the electron can be. All right, one is that we can have r less than r naught, right, which means that that test charge has been placed inside of this ball of charge. Right, so maybe we'll put it right here. Right, so this is 1. Right, maybe we have it there. Okay, and then the other option is r greater than r0. All right, so maybe the electron has been placed way out here instead. 2. Okay. And the question I want to ask is, what kind of forces, electrostatic forces, do these two test charges feel? All right, so how, in other words, what this means is what charge does an electron in the core feel versus what does the valence electron very far away feels, effectively. Okay? So let's do the easy one first. Let's do r greater than r naught, right? So it's far outside. Right? Right? So when the electron, now again, the electron's not an object, it's just a point in space, but imagine you can stand on an electron and monitor what it feels. What force does it feel? Well, from that distance, when it looks at the core, at the system, it just sees a giant ball of charge of approximately charge 1. Right? The whole thing just looks like all the electrons inside cancel out all but one of the positive charges in the nucleus. So at position 2, the charge that the electron feels an effective nuclear charge of approximately +1. Okay, so from the perspective of, let's say this 2 is like the 2s electron. It's in a new valence shell by itself. The 2s electrons are quite far away from the 1s electrons. From its perspective, it looks like it's orbiting something that looks like a hydrogen atom. Right? It's orbiting something of positive charge, of +1 charge. Okay, so from that perspective, it doesn't look like an atom of a +3 charge in the nucleus. It doesn't look like a lithium atom. It looks like the nucleus of a hydrogen atom. Right? And remember, so let's remember that the force that the electron feels, which is attractive, well, let's do the potential energy rather. Let's do the potential energy. The potential energy of the electron as a function of r is minus the effective charge of the nucleus times the charge of the electron, which is -1, so that's where the minus sign comes from, divided by 4 pi epsilon naught r. Okay, so the more charge you have, the more positive charge the electron feels, the more strongly attracted it is to that nucleus. Right? So what does that mean? That means that If the electron far away feels an effective charge of 1, then its potential looks very much like hydrogen. Right? It orbits and is attracted to this core exactly like the electron in hydrogen, or very, very close. But what happens when it's inside? Well, when it's inside, right, in position 1, it may not feel the entire set of negative charges from those electrons because it's in the same area as those electrons, the core electrons, right? So this test charge feels a slightly different, stronger charge because the cancellation of the Z-1 electrons hasn't been completely completed, And so it could be deep enough that it actually feels more of the positive charge from the nucleus than it would if it were outside of this circle. Right? So the closer that electron comes in, the closer to the effective charge it feels is closer to the actual value of the nucleus. And it turns out that when you do the analysis that the effective charge that the electron feels is a function of the distance. And it comes out to this formula here. It scales as 1 over r cubed, or r to the cube. So let's just kind of think about what happens on the different limits here. Okay, so when r goes r over r naught. So let's look at r over r naught equals 1. Right? So you're right on the edge of this circle. R over r naught equals 1. So you have z minus 1. The effective charge it feels is plus 1. Right? Just like we said. But as you start to bring r over r naught, as you start to bring the electron closer and closer and closer, let's take it to the maximum limit where r is 0. Right? The electron is right on top of the nucleus. Then the effective charge it feels is z. Okay, so so what happens is that the core electrons, right, this kind of soupy green mess of electrons inside the core, we say that they shield the outer electrons because because what they do is they cancel out at least some, or if not all but one charge, Porphyry charge, out of the nucleus. So as the electron gets deeper and deeper and deeper, it feels a stronger and stronger charge. But unless the core electrons shield it, and then that cancels out that effect. Right, so what we say is the implications here is that electrons in inner orbitals, or core orbitals, shield the nuclear charge from the valence. So when you go look at lithium, right, which is 1s2, 2s1, it's got one electron in the valence, and you look at the effective charge, you look at the energy levels of that electron and its excitations, and you can calculate roughly what the effective charge it feels is, you find that the effective charge that the lithium valence electron feels is very, very close to 1. It's a little higher than 1. It's about 1.3, I think. Right? And the reason why is because the 1s electrons in the core cancel out the majority of the charge of the 3 protons in the lithium nucleus. So what happens is that the alkali earths, right, lithium, sodium, cesium, I'm missing another one, beryllium. Is that right, beryllium? No, rubidium. Rubidium and cesium, all of these atoms act very hydrogen-like. Right? As we would expect from CHEM, they all have one unpaired electron. Right? We always say that the way that they want to satisfy and stabilize is to remove that electron and have a complete shell. Right? They all react fundamentally the same way. They all have very similar electron ionization energies. That electron takes roughly the same energy in lithium to remove as it does in hydrogen. And the energy level structures of these atoms look very similar to hydrogen as well. So again, this immediately leads to the fact that I'm literally deriving basically the idea of why the periodic table has trims to begin with. All the atoms in the same column have roughly the same amount of valence electrons, and therefore they're all roughly shielded by the same amount from the core. Therefore, they all act very similarly. Now, here's some interesting other deeper implications of this analysis. Is that we should consider how do, say, for instance, s orbitals shield versus p orbitals or d orbitals. And so, in fact, what we'll find is that s orbitals are very, very effective at shielding, and p orbitals are very poor at doing it. They're much worse at doing it. And let's analyze why that is. All right, so let's look at the orbitals. Or rather, I should flip that around. So what I should say is that electrons that are in s orbitals tend to feel a more higher effective charge than ones in p orbitals. I have my logic flipped. Sorry. So let me write that down. So electrons in valence s orbitals right? They can penetrate close. They have high probability or decent probability to penetrate towards the core. Let me explain why that is. So they can feel, electrons in s orbitals feel a larger ZF, effective nuclear charge, than other electrons since they can penetrate the inner core. All right, and why is that? Well, we just have to look at the wave functions for the s orbitals. So for an s orbital, let's just look at the one s orbital. So for hydrogen, well, let's look at the 2s. The 2s orbital, which again is just a function of r, looks like r to the e to the minus r over 2a naught. Okay, and again, when we want to measure where an electron may be, we got to take the square of it, right? We always take the square of the wave function. So psi 2s squared looks like r squared. Sorry, let me get rid of this r. I apologize. There's no r in it. Sorry, it's just e to the minus 2ra. Sorry. So this looks like e to the minus ra naught. And let me just say this roughly looks like it. So I'm missing some coefficients. Right? And so the question, of course, is what is the probability if the wave function looks like this? And of course, it's not normalized or anything. But what's the probability that we find the electron at r equals 0, right, in the core? Right? So the probability that we find the electron at r equals 0 is equal to e to the minus 0 over a naught, which is on the order of 1. All right, it's obviously not 1 because none of this is normalized. All right? But here's the important point, is that the 2s electron actually has probability distribution, some probability amplitude to be close to the nucleus. Right? So the s electrons tend to spend more time deep in the core, even when they're in the valence. They have probability to be in the core, close to it, and therefore they feel a stronger nuclear charge because they can penetrate those shielding electrons in the core and feel the effect of the nucleus. Right? That's why, for instance, in lithium, the 2s electron doesn't have an effective charge of 1, but it's closer to 1.3 or 1.5. Because the electron can sometimes, on average, exist inside of that 1s shell, closer to the nucleus, and therefore, on average, it feels a slightly stronger charge from a slightly stronger effect from the nucleus. Slightly higher charge. All right. Now, what about electrons that are in p and d orbitals, for instance, right? Well, what do we know about things that are in an L equals 0 orbital? So at orbitals with L equals 0, L greater than 0, excuse me, right? Or electrons that have angular momentum tend to have much smaller Z effective charges that it observes, that are close to 1. All right, and why is that, right? So this is like P and D. Right? And of course F's. Actually, they get better and they get closer and closer to 1 as you go to F and G. And why is that? Well, what we've done with these electrons is we've started to spin them. Right? L equals 1 means you have 1 unit of angular momentum. And what happens, right? So the idea is that the electron and the proton, the nucleus, are on a tether. They're on a tether, a weak tether, electrostatic tether. And so when you start to spin that electron, you orbit that electron, right? You apply, you get a centrifugal force to that electron, right? That pushes the electron away from the nucleus. Right? You have that centrifugal force that you feel when you spin. Right? And it causes the electron's position to stretch a little bit away from the nucleus. So typically electrons in these higher angular momentum orbitals, they tend to exist further away on average because they're driven further away. And right, you can it's not too hard to show, but the electrons here, right? And it's easier to see here is that the orbital for 2p, for instance, is a function of r. We're not going to worry about the angle part, just the r part here. Is proportional r to the e to the minus r over 2 a naught. And so when you square this, you get r squared e to the minus r over a naught. And so what's the probability at finding the electron in the core? Well, that's going to be equal to approximately 0 squared e to the minus 0, which is 0. Right, so electrons in s orbitals have probability to be near the core, but electrons in higher energy orbitals, r, p's and d's and stuff, they have no probability of being in the center because that angular momentum is pushing them away from the core. Right, so electrons in the p and d orbitals, they tend to be very effectively shielded by the deeper core electrons, and they basically are hydrogenic. They see a core that only has a charge of effectively +1. All right? This has consequences for the way that we add electrons and remove electrons from atoms. Right? You may notice that, maybe you've seen this when you've gone through the periodic table. If you've taken inorganic chemistry, you've certainly seen it before. But as you start to get down into the P's and the D's, you get into the N equals 3 valence, the N equals 4 valence. Right? You start getting into the D block. Electrons don't add into the orbitals the way you think they do. Right? You would think that they go from 1s to 2s to 2p to 3s to 3p to 3d to 4s. Right? They just go up in order like that, but they don't. And the reason why is because of shielding. So let me give you some examples of this. So let's look at argon and potassium. Potassium is the next atom after argon. So argon's electron configuration for argon 0 is 1s2, 2s2, 2p6, 3s2, 3p6, and of course, and so when you go to potassium, right, it's the next atom. So we add one more electron. All right, so if you would think just like kind of naively about the rules, right, we fill 1s, 2s first, then 2p, then 3s, and 3p. Right, we're done with the 3s at that point. Sorry, hold on a second. sorry, I apologize. Yeah, sorry. So you would think we would go into the D's next, right? Because that's the next set of orbitals. Right? N equals 3, L equals 2. But K does not do that, right? The electron configuration for potassium is argon 4s1. Right? And what's calcium? Calcium is argon 4s2. Right? We've skipped the 3d orbitals. Right? And it's not until the next atom, and I can't remember what the first one in the D block is. Let me pull out the periodic table really quickly. If anyone knows what's after calcium, let me know. I think it's vanadium. Scandium, sorry, scandium. Scandium is argon 4s2 3d1. Right? So the 4 s's get filled before the 3d's. Well, why is that? Well, it's because the s or the 4s electrons can bury themselves more deeply into the core. So they feel a stronger attraction to the atom. Right? There's a stronger attractive potential energy for the 4s electrons. Right? So 4s, so the idea here is that 4s penetrates more deeply than 3d, right? Because those 3d electrons are flinging themselves out really, really far away from the orbital, or from the atom. Therefore, the Z effective for the 4s electrons is greater than the effective charge that the 3d electrons feel, right? And that means, of course, that the attraction that the 4s electrons feel is larger than the 3d electrons, and therefore they're lower energy, they're more stable. Right? This implies that the potential for the 3s electrons, or for the 4s electrons, is less than the potential energy for the 3d electrons. Right? So 4s is more stable because it feels a stronger charge. Right? It's more attracted to the atom, the core of the atom, than the 3d electrons are. So the 4s's go first. And you'll see that that trend continues as you go down the periodic table. Now let's look at scandium for just a second. Right, so let's just do one more example, and let's just look at scandium. And the question I want to ask is, when we remove the electron, right? When we go to scandium plus, which electron gets removed first? So interestingly, so scandium to scandium plus, question mark, what's the electron configuration for scandium plus? Well, it turns out that when you do the analysis, scandium plus has a ground state of 4s1 3d1. It removes the s electron first. Isn't that strange? That seems to be opposite of what you would expect. You would expect the 3Ds to fill first, so they would leave last. But they don't. So you fill in the 3D, that gets filled in first. But when that 3D electron comes in, right, when you go from calcium to scandium, you add that D electron, it affects the shielding, it shields the 4s electrons. This is very interesting. So the 3D actually provides some additional shielding to these 4s electrons, which reduces the effective charge that the 4s electrons feel in scandium. And so when you go to remove an electron from scandium, you don't go to the potassium electron configuration, which would just be 4s2. You go to 4s1 3d1, because that 3d electron provides just a little additional shielding to that 4s electron, reducing the effective charge it feels from the nucleus, and thereby destabilizing it. I'll just kind of write that shortly. 3d electron shields 4s electron. And destabilizes it. So the energy ordering of the electrons in atoms are somewhat dynamic. They're not fixed. Right? Electrons, as you add more electrons into your valence, it starts to affect the other valence electrons. And as you get to higher and higher orbitals, those effects start to become more and more extreme. Because what happens is, remember, as you go up in n, the energy levels get closer and closer together. Right? The n equals 2 is the n equals 3 is closer to the n equals 2 than the n equals 2 is to the n equals 1. Right? The gap gets smaller. And so as you go up in the valence, electrons in different orbitals that are nearby each other in terms of their quantum numbers, 3 and 4 and s and d, they're closer together in energy and they affect each other more than if they were in 1s and 2s. Right there, the 1s and the 2s's, they don't talk to each other hardly at all. But once you get into the 3s and the 4s and the d's and stuff like that, things start to talk together. So the interesting thing is that when you go from calcium to scandium, right, you add an electron into the d orbital and add a proton to it. But when you go backwards and remove an electron, again, you're not removing the proton from scandium and go to calcium, you're just removing the electron. That 3d electron that you add destabilizes those 4s electrons relative to calcium and makes them less stable. So the electrons on scandium come off in the opposite order than they come on, as the electron configuration would suggest. Right? So all these electrons, they interact with each other a little bit. Electron-electron interactions are extremely important in atoms. But the nice thing is that you can think, okay, as I add electrons in these lower d orbitals, they will shield the 4s ones and destabilize them. And you see that across the trends on the periodic table. And you could take, and of course I'm only working on the left side of the periodic table here, but you get the same results on the right side of the periodic table as well, right? With the halogens, for instance. The halogens all act in a very, very similar way because they have one unpaired electron in the valence and 6 paired electrons in the valence. And those electrons basically, right, they're all in the same p orbitals. Right? The fluorine is in 2p, chlorine is in 3p. And these are just far away very far away valence electrons. They all act basically the same. And so the different halogens, they all have very similar spectra, very similar reactivity, because those 6 paired valence electrons in each of the halogens are all basically the same thing. They're all existing in similar orbitals, and therefore all the halogens act basically the same. The reason why, as you go down the halogen periodic table, that the reactivity does change, right? Iodine is a very weak base. Fluorine is iodine is a strong base. HI is a weak acid. If you think about the pKa's of these things, versus HF, which is a very strong acid, and F- is a very weak base, is due to the fact that as you go down the periodic table, the valence gets higher and higher and higher. It gets further and further away from the core, and they get weaker and weaker and weaker. Right? So the amount of energy it takes to remove an electron or add an electron, the halogen wants to gain one. So the amount of energy it requires to add an electron to chlorine or fluorine is more than it is to. Let me start over again. So let's look at the anions of the halogens. All right, so Cl minus, F minus, which means they have 8 valence electrons. So the energy to remove an electron from the anion is more expensive in fluorine and chlorine than it is in iodine. And of course, the reason why that is because those electrons are in deeper orbitals. Right? In fluorine, they're in the 2p. Chlorine, they're in the 3p. And then by the time you get down to iodine, they're in the 5p orbital. Right? And the 5p orbital is so damn far away from the core that there's basically no binding energy left anymore. It's a very, very loosely bound electron. So it's very easy to kick that electron out of iodine, but much harder to do out of chlorine or fluorine. Because those orbitals are much further away. They're lower energy, they're closer to the ionization limit, they're not as strongly bound. But the trends are the same, right? The reactivities are exactly the same. It's just that they're slightly different because, again, you're moving the n number from 2 to 3 to 4 to 5. You're pulling them further and further and further away from the nucleus. They become even more and more shielded, and therefore they're lessly bound to the nucleus, and therefore easier to pull off. Okay, this combined with Hund's rules basically give you allow you to fill out the periodic table. They give you all the trends. There's a couple of little intricacies in the D block where things get added, electrons get added in weird ways, and so there's an additional rule we have to consider for those D block elements where the electron configurations get weird. When you get to D block atoms, you can put 10 electrons in the D orbitals in the D block. When you get to a half-filled D block, which would be 5 electrons in the D block, it costs a lot of money, energy, to put another electron in pair 1 in the D6. And so sometimes that 6th electron will fill a different orbital. And that happens in some of the D block atoms. So there's a couple of other small little kind of niggling little details and little exceptions that you learn, but they're just on an atom-by-atom basis for the most part. Okay, and this constructs the periodic table from kind of a qualitative way. All right, and that's kind of all I want to say about atoms today. So what I want to do now, take a deep breath. What I want to do now is I want to put atoms together. Right? We have hydrogen atoms, but as you know, we don't often see hydrogen in its atomic form. Right? We usually, of course, in the universe, or sorry, on Earth, the only version of hydrogen we really see at room temperature is molecular hydrogen. Right? So what I want to think about now is what happens when we take 2 hydrogen atoms in these, where we have 2 electrons and 2 1s orbitals, and we combine them together. Right? What do the energy levels and what do the orbitals look like for the result of that? Right? How can we use our knowledge of the atoms to construct a new model for our molecules? Okay. So what we're going to do, again, just like we always do, is we bootstrap things up, right? We learned about hydrogen. We used what we learned about hydrogen to bootstrap the other atoms. Now we know everything we need to know about atoms. Let's take that information and bootstrap it into molecules by putting atoms together. All right, and this is what we're going to focus on for the rest of the class. All right? Talk about molecular orbital theories and molecules. And I do want to talk just very briefly, about a little bit of theory. Okay, we're not going to look at any Hamiltonians or any differential equations today. Not going to do any of that junk. But I think it's important to think a little bit about what does the physical system of, say, the hydrogen molecule looks like. Right? And that'll give us some idea of how to tackle this problem. All right, so we're going to talk about molecules today. Okay, so let's why don't we just try to figure out how to solve our problem, our quantum mechanical problem for the hydrogen molecule. Okay, so let's just start with H2. All right, so how are we going to construct H2? Well, we should start with 2 hydrogen atoms. All right, so we're going to start with 2 hydrogen atoms. In their ground state. So they're both 1s1. Okay, and we're going to put them at some distance r. Okay, and I'm just going to draw a little schematic of how we can think about hydrogen. All right, so there's going to be 2 nuclei. All right, so here's the first nuclei, H sub A. All right, it's just a proton, but this is just a proton. It's just the nucleus. And what we're going to do is we're going to connect it. We're going to draw a line between it and the other one, the other nucleus, HB. Okay, and the distance between these we'll call R. All right, so anytime I measure a bond length, right, because this is what that is, a bond length, assuming that we make a bond here. We haven't decided whether a bond happens or not. But the bond length is always the internuclear distance, right? And I call this big R, sorry. Okay, and so we also have 2 electrons in our system, right? So let's just put those electrons in here. Right, so I'll do them in a different color. Here's our electron on the first atom. We'll call this E1, or we'll call it EA. Now let me call it 1. I think it's better to have different labels. So E1. And then we'll put in another electron, which is the one for B, E2 here. Okay. And now, when we want to think about how to parameterize this problem, we need to measure all the little distances, right? Remember, our wave function is going to be a function of the inner atomic distances, right? We're going to have to consider how the electrons move, how the nuclei move with respect to each other, how the electrons move around the nuclei. So we should measure some distances. So the first distance we can measure is the inner electron distance. I did not want that to make a straight line. So we'll call this R12. Okay, and then we have some nucleus electron distances as well. All right, so one of them is going to be what we'll call R1A. There's one R1B. Right, and there's also cross ones, right? We can measure the distance from E1 to B, and we can measure the distance from E2 to A, R2A. Right, so we have all these little distances that we have to keep track in our molecule. It's a complicated problem. Right, we no longer function in hydrogen. We had just one. We had 3 coordinates, which are R, theta, and phi, but it was just a 2-body problem. Right, now we have 4 bodies. They all have 3-dimensional coordinates. Right, it's a complicated issue. All right, so how are we going to? We're not going to write any differential equations down, but remember, we want to solve the Schrodinger equation for this problem. So we want to write down an energy, right? We want to solve the Schrodinger equation. So let's just very roughly think about the different forces that are occurring. Right? What are the different energies that occur in a molecule? And this is, of course, very standard, right? Nothing changes if I go to a bigger molecule. If I draw benzene here, we just have more coordinates to track. But all the forces are exactly the same because there's just a bunch of nuclei and a bunch of electrons. So this is completely general. All right, so what are our terms? The terms of what we call the molecular Hamiltonian, right? The total energy of the molecule. Right? Well, we can just do a count, right? We can just count all the little distances we're tracking and think about the energies of the potentials energies as a function of those. Right? The first thing that we should do is think about the kinetic energies, like we always do, right? So there are kinetic energies for the electrons. So there's kinetic energies for E1 and E2. The nuclei are also moving. So we have kinetic energies for HA and HB. Right, so those are our kinetic energies. We're done there. Right, so that's all there is. There's going to be 4 kinetic energy terms that track the positions and the momenta of all four particles. But we have a lot of potential energies, right? Because there are 4 electroscatter. There are 2 positively charged elements and 2 negatively charged elements, and they're all interacting with each other. So there's going to be quite a few potential energy terms. Right? So let's just think about those a little bit. Well, first there's going to be electron nuclear attraction. Right? The electrons are attracted to the nuclei. And how many terms are there? Well, there's 4 of them, right? Because there's 2 two nuclei and two electrons, and they're all attracted to, well, each electron is attracted to each of the protons, or each of the nuclei, and therefore there's going to be four attractive terms, right? So there's going to be one for E1 and HA, E2 and HB, E1 and HB, and E2 and HA. Right? They all feel each other. Right? And then, this is 3, sorry, not 1. Right? And then we also have some repulsions, right? Because we have two electrons, and we also have two nuclei. They repel each other. Right? So there's an electron repulsion term. Which is E1, E2, and the coordinate for that, of course, is R12. And then there's a nuclear-nuclear repulsion, which is R. Okay, these are all the forces that our hydrogen atom, our molecule feels. Right? We've exhausted everything. Of course, we haven't included spin here, but we'll worry about spin right now. And spin will come later. Okay, but the spin, of course, as we saw in the hydrogen atom, the spin affects the energy very, very lightly, not much. Very small amount of energy. Right, so we have all these terms, right? So we can write a big Hamiltonian. Right, we could say the total energy of the system is 4 kinetic energy terms plus 4 attractive electrostatic potential terms and then 2 repulsive ones. Right, so we have 2 positive energy terms where kinetic energy is positive, 2 positive potential energies, and 4 attractive energies, electrostatic potential energies. Right? And so you can write this all down. You can get a Hamiltonian, and I won't write it down because it's a waste of time. Right? Because I'd rather teach you, I want to get right down to the nitty-gritty, which is that when you write the Hamiltonian for this and start thinking about the wave functions and solving the Schrodinger equation, you can't solve this. It's unsolvable. The Schrodinger equation cannot be exactly solved for this problem. So the problem here is that H psi equals to E psi is not solvable exactly for this problem. All right, and it turns out that there's one term, out of all of these terms, energies, there's one term that throws everything in the garbage, right? If we could get rid of this one term, everything would solve normally and it'd be great. We could write it down on the board, we can write the wave functions down. And I might show you on Monday this example. I'm not going to move on, but we'll see. But if I can get rid of one of these terms, everything works perfectly and I can solve the Schrodinger equation on paper. And the one term that kills us is this electron-electron repulsion. So the reason why is that the term... Oh, yeah, see ya. The potential for VR12, which is E squared over 4 pi epsilon naught R12, where R12 is the distance between them. Right, so this is what the potential energy operator looks like for this term. This is a function of both R1a and R1b. Okay, so as one electron moves, all right, so imagine that E1 starts to rotate around the proton this way, counterclockwise, right? It starts to move around into the internuclear axis. All right, well, how is electron 2 going to adjust? Well, electron 2, remember, electron 2 wants to be as far away as possible from electron 1. So if electron 1 comes down this way, electron 2 is going to move the other way, right? But what if electron 2 moves separately? Then it's going to affect where electron 1 goes, right? The two positions are correlated to each other perfectly. The electrons have to be at maximal distance from each other at all times. So this potential is a function of both coordinates simultaneously. It's a function of both positions. And what you can show, so instead let's just do something really quickly. Let's say the position of these atoms right here, or these electrons, sorry, are R2 and R1. Okay? So we can just track the positions of the electrons. What you can show is that the commutator between, say, R1 and R12, or let me call it V of R12, is not equal to 0. Right? And what does that mean? Well, that means there exists no wave function exact wave function that allows us to measure both the electron position and the distance between the electrons. Okay, so we can measure one or the other. We can either measure each of the electrons moving independently of each other as if the other ones don't exist. Right? We just assume that they don't know each other. They're just completely and they completely have no knowledge of each other. We can solve that problem. Turns out that we can also solve a problem where we just assume we don't know anything about the positions of each electron, and we just parameterize everything relative to the distance between the two. You can solve that, but you don't learn anything useful from that, because it doesn't really tell you anything about where the electrons lie in terms of the atoms. We lose all information about the atoms when we do that, because the system is now defined as a relative position between two electrons. You have no idea where those electrons are. They could be anywhere. Because if they're 1 angstrom apart, that could mean that they're both on the same atom 1 angstrom apart. They could be both on 2 different atoms 1 angstrom apart, right? They could be anywhere. So you don't learn anything about the structure of the molecule like this. So the problem now is that there's no way to solve this exactly because of this problem. There's no way to get the information we want, which is what do the electrons do and where do they exist together. We want to track the electrons, but we also want to measure their interactions between each other, because of course they repel each other. So the first thing that we could try, as I said, was we could just get rid of this, right? We could assume that they're not repelling each other. That seems like a reasonable thing. Maybe the electrons don't see each other at all. Maybe they're just always far apart. Right? And when you do that, you get the wrong answer. And in fact, when you calculate the energy, the bond strength for hydrogen, assuming that the electrons don't repel each other, you're off by like orders of magnitude. All right, it's the wrong assumption. I wouldn't call it orders of magnitude. So maybe you're off by a factor of 3 or so. All right, repulsion plays electron-electron repulsion plays an extremely important role in molecules. So we have to account for it. If you don't account for it, you get the wrong answer every single time. All right, so we have to come up with a new approach. All right, we'll figure out something. Some way that we can approximate, right? So we can't solve this exactly, but maybe we can make an approximation. Or maybe we can make a guess. All right? And simplify a few things. All right? And see if that fixes our problem. And see if we can get a good guess starting, and then we can make our guess a little bit better each time to improve our estimates. All right? So we're going to instead have to approximate. All right? And the entire world of computational chemistry. If you're a 4+1 and you take computational with Professor Zhao next year, you'll see this. He probably talks to you a lot about this. So the entire field of computational chemistry is built around this concept that we have to make approximations here. And pretty much all of methodology development in computational chemistry is about coming up with new ways to approximate this. Right? Come up with better ways to guess the structure of an atom or structure of a molecule, find these approximations that allow us to then calculate a molecular structure. Right? Because we can't solve this problem exactly on paper. Right? We can solve it for a system of one electron. But the moment we add 2 electrons to a system, we can't do any more paperwork. Right? We have to make approximations. So what I'm going to teach you for the next 2 weeks is this approximation. At least one of them. There are many different ways to do it. I'll teach you the most common way to do it. You may have heard of the term, what I'm going to teach you is what's called, well, let me just get to the next page. So what we need to do now is we need to approximate an approximate system, our approximate model, to estimate our energy and wave functions. Okay? There are many different ways to do this. Right, one of the most common ways that chemists and physicists and engineers approximate molecular structure is using something called density function theory. All right, I'm not going to teach you DFT in this class because we're close to talking about DFT. The materials people that look at solids, crystals, things like that, they use something called plane waves. They come up with this unique way of using waves, oscillations and electrons in their materials called plane waves, and they can solve the Schrodinger equation by assuming that the orbitals look like waves, oscillations in the material. Right? So they use this they basically treat the orbitals like oscillating amplitude waves that are propagating along the surface. Right? These are like little drum, like fundamental modes of a drum. Right? Little oscillations, unique oscillations of the material. So we're not going to learn these two. And DFT is very, very common. It's used by everybody. But it's kind of a complicated thing. So what I'm going to teach you instead is an older methodology, which is still used today, but it's much more useful pedagogically. And it also gives us a much better way to qualitatively calculate molecular properties. And it was developed It was the first way that people came up with a way to solve the Schrodinger equation for molecules. It's the original. And it's quite useful. It turns out that as you make the approximations better, it scales very, very poorly. It gets increasingly more and more and more complicated and expensive to do the calculations. And I'll show you some examples of that next week about how to do this in practice. So what we're going to learn today, or we're not today, but what we're going to focus on is this method. So the approximation method we're going to use is called linear combination of atomic orbitals which we notate LCal dash molecular orbital theory. So this is often called LCal-MO. All right? So what we're going to do is it's literally, the title is very descriptive. We're going to take combinations of atomic orbitals that we know, right? We know what the 1s orbital for hydrogen looks like, right? We have an idea of what that atom looks like. So what we're going to do to construct our H2 molecule is put a hydrogen in the 1s orbital here, put a hydrogen in the 1s orbital here at some distance, and assume that the resultant wave function of the molecule is just the product of the two. We're just going to add them together. All right, we're going to do psi1 plus psi2, two 1s orbitals together. All right? When we do that, we can solve. All right, so let me just say that. So let's think about this kind of in a kind of holistic way. All right, so let's think about hydrogen here for a second. All right, so we're going to choose two 1s orbitals. All right, so here's HA. It's in a 1s state. And we're going to put it at a distance r. Which is also in the 1s state at some distance r. Okay? And the way we're going to solve this problem is that the Hamiltonian for H2 is going to be the Hamiltonian for the A atom. All right, so it's a hydrogen orbital plus the energy for the B atom plus a term that's small that mixes the two. All right, so we call this there's different terms for this, but we'll just call it the mixing term. And we're going to assume that HAB, the value of it, like basically the energy of it, is much, much smaller than the sum of the energies. So let me write it like this. EAB is much, much smaller than EA plus EB. All right, the idea is that the Hamiltonian applied to the wave function for the A atom gives us EA times the wave function back, and it does that for B as well. All right, so each of these little Hamiltonians solve the Schrodinger equation for hydrogen and give us an energy. And then we have this small mixing term that we add. All right, and this mixing term, and this gives us EAB. And that the Hamiltonian for this EAB is proportional to plus E squared over 4 pi epsilon naught R12. And the way that we're going to measure this energy is by taking an average value of it over our atoms. So we're going to put our two atoms there, and just like we do in the intensity calculation on the midterm, we're going to take our two atoms that are different positions or different states, and we're going to add this little connective tissue, right, this connecting term, and we're going to evaluate the average value of that across the two states. Right, so EAB is going to be the integral, well, it's a triple integral over the sphere of the wave function for atom A, which is a function of the electron with position r sub A, times our operator. And let me just write one more thing. I'm going to write R12 as the absolute value of the distance between the two electrons, RA and RB. So we're going to have an operator that looks like that. And we're going to multiply it by the orbital for the B electron in the B atom. And then, of course, integrate over all space. So I'll write dV. Right, this is the sphere, dV. Right, so this is just like what we do in the midterm, right? In the midterm, the way that we calculate the intensity of our transition between two states is we took our intensity operator, our dipole, right? We measured the average value of the dipole across the two states. So we're doing the same thing here, except we have our two states are two different atoms with two different electrons. And we're measuring the average repulsion between them. Right? So we're going to average the repulsion energy. Right? So we're going to it's just going to be a number. All right, so this is the average repulsion energy for electrons at positions RA and RB. Okay, so what we're doing is we're solving the hydrogen molecule problem, assuming that we have two separate atoms that don't interact with each other. Okay, and then we're going to include a little interaction term. Okay, so we're basically what we're doing is we're starting with a state that's two independent atoms, and we're just going to perturb them a little bit by adding a little repulsion between them, and we're going to assume that that repulsion is much smaller than the actual energies of the electrons. So basically, the repulsion only affects the electrons a little bit compared to the normal behavior, right? We call it a perturbation, right? It's just perturbed a little bit. It's not completely screwed. It hasn't completely been, its day hasn't been completely ruined by the repulsion. It's just been changed a slight amount. And what we're going to do is assume that the contribution of that, the energy contribution of that, is just the average over all space. All right? So we're going to average over all the different orientations of these two electrons with respect to each other and calculate their average position and their average repulsion and just take an average. Okay, so we're not doing an exact measurement, right? I'm never going to have a coordinate that looks like the distance between these two. I'm just going to integrate over all possible combinations of RA and RB and figure out what the average repulsion energy is. Okay, so we're instead of doing a problem that has that distance coordinate R12 as a coordinate of the wave function, our wave function is going to be a coordinate of our two atoms independently, and then their energy is just going to be affected slightly by this average repulsion energy. Right? There's a term for this. Right, so the idea is that we're just averaging out and statistically measuring the statistical effects of the repulsion. And there's a term for this. It's called, let's pull it over here. This is called mean field theory. All right, and it is the fundamental motivating principle for all of chemistry, all of computational. Because the fact of the matter is, the moment you have two electrons, you can't know both of their positions simultaneously if we assume that they're perfectly correlated to each other. You can't know them. And so what we're going to do is we're going to assume a system where they're separate from each other, and we're just going to assume that they touch each other every once in a while, and we're just going to measure the average. Okay, so the wave function that we get is still just a function of RA and RB, but the energies have been manipulated slightly by the effect of this repulsion. Okay, so we have this electric field of repulsions, and we're taking the mean of it. That's what mean field theory is. And we're just going to assume an average. We're just going to average over it. Right? We're never going to do this math. I just wanted to talk kind of basically about it. And now the question, of course, is, all right, so the energies are changed slightly due to repulsion. What's the net effect on the wave functions? All right, so let me talk very briefly about that. Okay, so I'm going to look at this in a kind of an interesting way. We're going to go back. I think the best way to look at this effect is by, let me think about this. Think of the best way to do this. Oh yeah, here we go. So our net Hamiltonian So our Hamiltonian for our H2 molecule has two atomic terms, right? These are hydrogen Hamiltonians. plus a small correcting term. So write that in really small text, HAB. Right? And when you solve the Schrodinger equation for this problem, so when we solve the Schrodinger equation, we just solve it for this unperturbed part. So we solve this, which we can do. So solve for wave functions. And the wave functions for this system, so for H2, will look like the wave function for A, so position of RA, theta A, phi A, times the wave function for the B electron. Right? We just multiply the two hydrogenic orbitals for each one. And all of these orbitals are, sorry, this is B, I apologize. Right? This is just the 1s orbital for hydrogen. Right? So the resultant wave function for hydrogen, the molecule, is just a product of the two atomic orbitals at some distance from each other. All right, we just take a product of them. Now, here's a problem. What happens when I swap the electrons? I mean, what if I switch A and B together? What if I exchange the electrons? Remember, electrons are identical. Right? So there's really nothing different between electron 1 and electron 2. Nothing different. So there's no reason for me to be able to exchange them. Right, so what happens, for instance? Right, so our initial state was, so let's swap electrons. So what we call this is exchanging, what we call exchange electrons. Okay, so what we're going to do is we're going to take psi A, R sub A, times psi B, R sub B. And I want to know what happens to my system when I go to psi A and I put it at R sub B. Right? So I put the B electron in the A atom and the A electron in the B atom. So when this theory first came up in the 1930s, people assumed that the proper wave function for H2 is this, just this. It's just two, remember these are even functions, right? These are even functions. Right? So when we exchange electrons, so we have an even function times an even function. So the overall function is even. So people thought initially, well, when I exchange electrons, I just get the same thing back, right? I get a plus sign. Right? Once you exchange electrons, it's like changing axes. You get a plus sign. Right? This is the assumption. Right? We say they're symmetric about exchange. And so you can take this and then go calculate the energies of the helium atom. And in fact, in my notes, I do this approximation for helium because you also have this problem in atoms. When you get two electrons in an atom, you can't calculate it. You go look at it in helium, and it gives this assumption, right? You assume each of the electrons in helium is a hydrogenic 1s orbital, and therefore your helium wave function is just a product of these two 1s orbitals. And you go do the math, calculate the energies, the repulsion energy, all of that junk, do the integrals. You get the wrong answer. It's off by a massive amount. Right? This doesn't work. Symmetric exchange is wrong. Okay, so when you change electrons, you exchange electrons, which happens all the time, right? In a molecule. Electrons can just exchange. They can replace each other because they're all identical. There's No real reason why A has to be A and B has to be B. When you do this manipulation, you get a negative sign instead. So when you do experiment, when you look at experiment and you do the theory, experiment shows that when you exchange two electrons, you get a minus sign. The wave function changes signs. So we say that they're antisymmetric. And I'm done after this in just a second. I just want to set up my question for Monday. They're antisymmetric exchange. So how the hell does that antisymmetry come up? Because these are even functions, right? Our molecular orbital or orbital for the molecule is just a combination of two even functions. They should exchange just fine. But there's a negative sign. Right? We have to figure out where that negative sign comes from. Once we figure that out, we'll actually be able to come up with a better version of this wave function. And that will immediately lead us to an accurate representation of the orbitals and the energy levels of molecules. Okay, so we have to figure out what this negative sign is, and it's the key to everything. Okay, so on Monday we'll come back to that. All right, this snake, I'll just write that for you guys if you want to read it later. Anyway, have a lovely weekend. Homework's due on Friday. If you guys feel like you're not done with it, just take your time. I won't be grading until next weekend. Oh, you can take your time on it if you want. Please come to my office hours if you have any questions. And I'll have the final homework out for you guys hopefully by Wednesday.
We have to make posters and stuff for the actual event, and like write what the tab means.
You too, thank you.
See you Friday.
I see you Friday.
Bye, have a nice day.
Bye, you too, thank you.